Okay guys, this is 11.1, the chi-squared test for goodness of fit. I had a little background noise, so we're just going to start from here. This is our formula. This is chi, and it's going to be squared. It is the sum of the observed counts minus the expected counts. We're going to square that difference. We get a positive value, and we're going to divide it by the expected. Now, the reason why we want to do it this way is so that when we get a difference of value and they're pretty close to being the same, which is kind of crazy to think about, if we square it and divide, this right here could we come up pretty close to being the same, but then when we divide it by the expected, we actually get something that's going to allow it to be a little bit more influential, which we'll show you here in a couple minutes, okay? It'll make more sense when you see it, but we'll go from there. Now, our degrees of freedom, this is our chi-square graph. The first one, degrees of freedom 1, is an exponential decay function. It just drops down like crazy. Okay, we hit degrees of freedom 2, and it starts to get a little bit of a right tail skewed, which we see. Our degrees of freedom 5, we still have right skewed, but that heel is not as sharp, and we still get everything a little bit balanced out. The same rules apply here, is that our density curve, it's going to add up to 1. So the percentages in here are going to add up to 1. Okay? Now, our degrees of freedom are the different multiple characteristics. Okay? So what we can think of is M&Ms, right? So we have red, blue, yellow, green, and brown. Oh, and I forgot orange. How dare I? All right. So, are those colors evenly balanced? Well, I don't know about you guys, but every time I open up a bag of M&Ms, I seem to get a majority of brown, right? So, does that tell the truth? And so, Mars, and we would have done this in class, but Mars candy actually comes out with a way of how many are actually brown, blue, and they tell you their actual percentages, and you get to go through it, okay? And we would have found out something like that, and each year it's been different. So, maybe we'll try and do this as a final project, but we'll keep going, all right? The chi-square test compares observed to expected counts, not proportions, okay? Don't do this for proportions. It's got to be a count, okay? Even though it might be a decimal, we still got to be able to count it, okay? Now, the idea of the chi-square test of goodness of fit is we compare observed counts as our sample to expected counts are theoretical. The further our observed count is from our expected counts, the more evidence we have against H naught. So we would reject H naught. Okay. Now, to kind of explain all this and everything like that along the line, I thought we would start with just this example and try and explain it as we go along. All right, so does your zodiac sign predict how successful you'll be in life? A Fortune 500 magazine article collected the zodiac sign of 256 heads of the largest 400 companies. Okay, so we're asked, being born in a certain month, is that going to mean that you're more successful than everything else? Okay. So what I'm going to do is I'm going to show you the chart. Just a second. Okay. So here is the data from our Fortune 400 magazine. We've got Aries, Taurus, Gemini, Cancer, Leo, Libra, whatever, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. Sorry guys, it's been a long day. Anyway, so this is our observed counts. Okay? Our expected counts is taking our 256, which is our total amount, and we're going to divide that by 12. Because how many different things do you have? 12. So we expect this to be 21.33. Okay? So to kind of do this not necessarily the long way, but just so you can see it by hand, this column right here would be our expected account, our expected counts. So then there would be 21.33 all the way through. All right. Now, the next part that we have for our formula is we're supposed to do our observed minus the expected. Okay. And so I've already did this, so we're just going to write them down real quick. We got 167, or 1.67, negative 1.33, negative 3.33, 1.67, negative 1.33, negative 2.33, negative 3.33, negative 0.33, negative 2.33, 0.67, 2.67, and then 7.67. Okay, so this is going to be our observed minus our expected, and then we're going to square it. So all we're going to do is we're going to come into here and we're going to square this column. So that means that if it's negative, it's going to become positive. All right, so this becomes 2.7889, 1.7689, 11.0889, 2.7889, 1.7689, 5.4289, 11.0889, 0.1089, 5.4289, 0.4489, 7.1289, 58.829. All right. So then what happens next is we take O minus E that's been squared and we divide it by E, our expected value. So we're going to take this and divide it by 21.33. So I get 0.1308, 0.0829, 0.5199, 0.1308, 0.0829, 0.2545, 0.5199, 0.0051, 0.2545, 0.0210, we have 0.3342, and then 2.7580. All right, so what we're going to do is we want the sum of our observed minus our expected divided by our expected. Okay, so we're going to add this whole column up. Okay, so when I add it up, I get 5.0945. Okay, now what we're looking at is, hey, what does that tell us? Well, this is our chi-square value. All right, so that means we're going to go to our table and we'd come down here, degrees of freedom are 11 because we had 12 items, so 12 minus 1 is 11, and I'm looking for the 5. And if I keep looking, it's getting bigger and bigger as I go further and further away. Okay, so If I come back down to here, it's 13.70. So that's telling me that that our value's got to be bigger than 0.25. Okay? So my p-value, our p-value is greater than 0.25. Now, if we were doing a real significance test, and we're going to talk about our hypothesis in just a minute, we'd come into here and say, okay, what about 0.05? That's what we normally test. That's our this is a significance test. We're just doing a significance level of 0.05. Well, our p-value is greater than 0.25. We don't know where it is yet because we're only using the table. Well, if you put this into here like this, right? What happens? I know I'm giving you too much. Then we're going to fail to reject, right? So then we would reject our we would fail to reject our null hypothesis. So that means that we kind of accept it or realize that there's not enough evidence to prove that it's wrong. Okay? So what we're going to do is we're going to stop here and make the next one real quick, and we're going to talk about how to write out a hypothesis, our null hypothesis, and an alternative hypothesis, and then we're going to do another example so that we can talk about how to actually carry out a good test for everything. Okay?